Section 10.5, Graph Theory. A directed graph is a finite set of elements, P1 through Pn, together with a finite collection of ordered pairs, Pi, Pj, of distinct elements of the set, with no ordered pair being repeated. The elements of the set are called vertices, and the ordered pairs are called directed edges. So here's a bunch of vertices, and here's a bunch of directed edges. The entire thing is the directed graph. We use the notation Pi to Pj, which is read Pi is connected to Pj, to indicate that the directed edge Pi Pj belongs to the directed graph. Geometrically, we can visualize a directed graph by representing the vertices as points in the plane and representing the directed edge Pi Pj by drawing a line or arc from vertex Pi to vertex Pj with an arrow pointing from Pi to Pj. If both Pi to Pj and Pj to Pi hold, so that means that we have this double arrow, we draw a single line between Pi and Pj with two oppositely pointing arrows, like right over there. So with a directed graph having n vertices, we may associate an n by n matrix, M equals Mij, called the vertex matrix of the direct graph, as elements are defined by Mij equals 1 if Pi points to Pj and 0 otherwise. As an example, a certain family consists of a mother, a father, daughter, and two sons. The family members have influence or power over each other in the following ways. The mother can influence the daughter and the oldest son. The father can influence the two sons. The daughter can influence the father. The oldest son can influence the youngest son, and the youngest son can influence the mother. We may model this family influence pattern with a directed graph whose vertices are the 5 family members. If family member A influences family member B, we write A points to B, determine the resulted directed graph and vertex matrix of this directed graph. So how about we start with the mother? We'll make a little vertex right over there, and we'll point that to the daughter. Actually, sorry, I'm going to put my arrow in the middle. So we'll call that the daughter, because the mother can influence the daughter, and the oldest son. Put that right over there for oldest son. And then the father can influence the two sons. So I'll put the father over here, but the mother influences the older son, and the father also does. So I'll put opposite arrows. So this will be father. And the father influences the youngest son. I'll put the youngest son up over here. Doesn't really matter exactly where you put each of these guys as long as they all line up together properly. And then we have that the daughter can influence the father. So daughter goes to father. And then the oldest son can influence the youngest son. And the youngest son can influence the mother. Okay, cool. So now let's build our vertex matrix. So we'll have the mother, father, daughter, oldest son, youngest son, and we'll also have those for columns. Mother, father, daughter, oldest son, youngest son. So the mother can't influence the mother, can't influence the father, can influence the daughter, can influence the oldest son, but not the youngest son. And then the father can influence the oldest son and youngest son only. And then the daughter cannot influence the mother, but can influence the father, and can't influence the daughter, the oldest son, or the youngest son. Oldest son can only influence the youngest son, and the youngest son can only influence the mother. And then there we go. That's our vertex matrix. Let's do another example. In chess, the knight moves in an L-shaped pattern about the chessboard. For the board in the top figure, it may move horizontally 2 squares and then vertically 1 square, or it may move vertically 2 squares and then horizontally 1 square. Thus, from the center square in the figure, the knight may move to any of the 8 marked shaded squares. Suppose that the knight is restricted to the 9 numbered squares in the bottom figure. So I'll say that the night can only be restricted to those 9 squares. And if by I to j we mean that the night may move from square I to square j, let's determine the resulting directed graph and vertex matrix that illustrates all possible moves that the night may make among these 9 squares. So say we started the night in square number 1. Well, then they have to move in an L shape according to the top picture. So that means that the night would have to move to 8, or the night could move to 6. Right? Because it could either go down 3 over 2, or it could go down 2 over 3. There's no way it could move up. There's no squares over there. It can't move to the left. And so these are really the only 2 possibilities. So what I would write is vertex at 1, and I'll draw an arrow. Well, how about I list them out, actually? Maybe it'll be easiest to do it that way. So I'll write 1, 2, 3, and I'll put vertices, and then 4, 5, 6. And I'll put 4 over here so that it doesn't bump into anything. And I'll put 7, 8, and 9. Okay, so now I'll try drawing my arrows. So I have to go from 1 to 6. So I'll put an arrow going from 1 to 6. And I have to go from 1 to 8. And there's nowhere else to go for that. What if we started at 2? So then we could go down to 7. We could go down to 9. And that's it. So go to 7. And I'll go to 9. And then if we started at 3, we could go to 4, or we could go to 8. So 3 could go to 4, or 3 could go to 8. All right, how about if we started at 4, then we could go up to 3, or down to 9. So I'll draw another arrow the other way for 3, and draw one going to 9. Then if we started at 5, doesn't look like we have enough room to go anywhere because we have to go over there off the board in any direction that we went. So there's no possible vertex that connects to 5, so I'll just leave that blank. And then for 6, well, I could go down or up. So I could go to 7 or 1. So I'll draw 1 at 1, and I'll draw 1 at 7. And then at 7, I can go to 2 or to 6. So I'll draw 1 going back to 6 and to 2. And then for 8, 1 or 3. So draw 1 going back to 1 and to 3. And then for 9, we can go to 4 or to 2. So I'll go to draw a little arrow at 2 and a little one at 4. Okay, great. The only issue with this picture is that it's a complete mess. It's very hard to see. So by reordering the vertices a bit, we can kind of unravel the picture if we're careful. I can put a vertex at 1 and see that that connects to 6 and 8, so I'll put 6 and 8 adjacent. And 8 connects to 1 and 3, so I'll put 3 next to 8. And then 4 connects to 3 and 9, so I'll just go to 4 and then down to 9, which connects to 2 and 4, so I'll put a 2, and 2 goes to 7 and 6, so I'll just put 7 in between them, and then I can connect like this, so I can, 1 goes to 8, but 8 also goes to 1, which goes to 3, which also goes. Each of these go to each other, so it's just like one big happy circle. And that makes it a lot easier to see what's going on. So both of these pictures represent the same graph. Okay, so now let's do our matrix. Let's call that M, and for the first one, 1 can clearly go to 6 or to 8. It's a lot easier to see that now. So I'll put zeros in all of the other columns, and I'll just go from 6 to 8. So 1, 2, 3, 4, 5, 6 is a 1, and then another 1 for 8. So then 2 goes to 7 or 9. So 0, 0, 0, 0, 0, 0, 1, 0, 1. Then 3 goes to 4 and 8. So we'll put that in. And 4 goes to 3. And 9. Oops, I put 9 instead of 8. There we go. Okay, so we have 3 and 9. And then 5 goes to none of them. And 6 goes to 1. And 7, 5, 6, 7. And 7 goes to 2. And to 6. And 8 goes to 1 and to 3. And then we just have 9 going to 2 and to 4. Okay. And there's our vertex matrix. Wonderful. We call PI to PJ in a directed graph a one-step connection, and PI to PK to PJ a two-step connection. Similarly, we call PI to PK1, PK2, etc. an R-step connection. So in our graph, you can see that this thing goes over here, which then goes over there, which then goes over there. Let's see. So this is 1, 2, 3, 4, 5, 6, 7, 8 step connection, roughly. Unless I miscounted. Let M be the vertex of a directed graph, and let Mijr be the ijth element of MR. Then Mijr is equal to the number of R-step connections from PI to PJ. The figure is the route map of a small airline that services the 4 cities P1, P2, P3, and P4. Let's find the number of 1, 2, or 3 step connections from P4 to P3. So first let's draw our matrix M. So we have that P1 goes to 3 and to 2. So I'll put 0, 1, 1, 0, so it goes to 2 and to 3. 2 goes to 1, doesn't go to 2, and it goes to 3, and not to 4. Then 3 goes to 1, and not 2, not 3, and to 4. And then 4 goes to 2 and to 3. So that's M. So that means that M for 3 is equal to 1, because that's the 4th row, 3rd column. Okay, so that means that we have, by the previous theorem, one-step connection. To find the 2-step connections, we have to square M. So we'll write M squared. If you want, use a calculator or just do it yourself. In any case, I'm going to omit the work. We get 2, 0, 1, 1, 1, 1, 1, 1, 0, 2, 2, 0, 2, 0, 1, 1, which tells us that M4, 3, 2 is now, oops, that's not the 4th row. There we go. 4th row is a 1 again. So we have one two-step connection. Okay, so now let's cube it to find the three-step connection. So m cubed is 1, 3, 3, 1, 2, 2, 3, 1, 4, 0, 2, 2, 1, 3, 3, 1. So let's look at what M433 is, and it's 3 in this case. So we have three three-step connections. So let's see if we can figure out what they are from the picture. Well, going from P4 to P3, that's our one-step connection that we got. So for the one-step connections, we just have, remember we're going from P4 to P3, we just have P4 to P3. Okay, how about the two-step connections? We were told, or we determined, that there should be one of those also. And we can figure it out. Let's see. So we want to go from P4 to P3, but we don't want to go direct. We want to stop along the way. And it looks like the only way to do that is to go from P4 up to P2, stop there, and then go to P3. And that'll be in 2 steps. There's no other way to do it in 2 steps by the picture. So we'll go from P4 to P2 to P3. And that's our 1 2-step connection. Now we should be able to find some 3-step connections. We determined that there should be 3 of those in this case, from P4 to P3. And let's see if we can find them. So we could go from P4 to P3, and then go back to P4, and then go back to P3. And that would be 3 steps. So that counts. So let's write that. We can go from P4 to P3, back to P4, back to P3. So 3 hours, 3 steps. Okay, how else could we do it? Well, let's see. We could also go from P4 to P2, and then go to P1, and then P3. It's kind of a natural 3-step connection. So we could go from P4 to P2, P1 to P3, and there should be one more because we saw it was 3. So how about we go from 4 to 3, and then go from 3 to 1, and then go back to 3. That'll be 3 steps. And that's the last one from the picture. So we'll go from P4 to P3 to P1 to P3. A subset of a directed graph is called a clique if it satisfies the following 3 conditions. The subset contains at least 3 vertices. For each pair of vertices pi and pj in the subset, both pi and pj, both pi to pj and pj to pi are true. So it needs to go back and forth between those 2. And the subset is as large as possible. That is, it is not possible to add another vertex to the subset and still satisfy condition number 2. So let's do an example. What are the cliques for the graph illustrated in the figure? Well, it's kind of a complicated figure, but we want to make it as big as possible in the sense that each of the vertices that we're throwing in our clique has to connect to another vertex and back to itself. So P1 goes to P4, and P1 goes to P3. Those both go back to the double arrows for both of them. And P1 also goes to P2 with a double arrow. And we have to make sure that P2 also goes to P3, because if it's going to be in the click, it has to go every single one. And P2 has to also go to P4, and P3 has to go to P4. Great. So it looks like that should be a click. So let's write that out. P1, P2, P3, and P4. That's a click. We can't throw in P5 because it doesn't go back to P3. We can't throw in P6 because it doesn't connect to the other members of the click, and same reason for P7. However, there is one more click in the picture, and that's right over here. Where's it? 3, 4, and 6. Because all of these guys go back and forth between each other, right? So let's put that click in there. P3, P4, P6. We can't just say that 3 and 6 are a click, because it's not as big as we could make it. It's possible to include 4, so 4 has to be in there. The matrix S equals Sij related to a given graph is defined as follows. Sij equals 1 if Pi goes to Pj and Pj goes to Pi, and 0 otherwise. So this is how we can identify clicks. Let Sij3 be the ijth element of S cubed, then a vertex Pi belongs to some click if and only if Sii3 is not equal to 0. So let's prove that real quick. If Sii3 is not equal to 0, then there is at least one 3-step connection from Pi to itself in the modified directed graph determined by S. Let's suppose that it is Pi goes to j, goes to k, goes back to I. In the modified directed graph, all of the directed relations are two-way. So we also have the connections Pi goes to Pj, which also goes to Pk, which also goes to Pi, and back. But this means that Pi, Pj, and Pk is either a click or a subset of a click. In either case, Pi must belong to some click. The converse statement, if Pi belongs to a click, then Sii3 is not equal to 0, follows similarly. You could prove the converse, and then you get both, and that's how you get your if and only if. So let's suppose that a directed graph has it as its vertex matrix, M given in this example. What are the clicks of the directed graph? So what we can do is just compute S. So we need S to be, it's kind of going to be basically M, but instead of having, it's going to have all of the zeros that M has, or not a zero, all of these zeros it'll have, and it'll have some of the ones, but it'll only have a 1 if that's a vertex that goes back to itself. So in other words, for this first line, let's say that was A. Maybe this is A, B, C, and D. Call this A, B, C, and D. Then we have A goes to B, but we also have that B goes to A, because there's a 1 over here. So we have A goes to B and B goes to A, so that means that these 1s will stay. However, we have A goes to C, but there's a 0 here for C going to A. So that means this C, this 1, will be replaced with a 0. So that's how we can build our S. All the zeros will stay, so the top left 0 stays. The first one stays, as we saw, but then there's a 0, and this last one will stay because if this was D, then A goes to D and D goes to A. So that one will stay. So we'll have 1, 0, 1, 0, that will stay. Then we'll have 0, 1, 0, 0, because C goes to D, but D does not go to C, as we could see. So 1, 0, 0, 0. And that's our S. And now we can cube it, and we'll get 0, 3, 0, 2, 3, 0, 2, 0, 0, 2, 0, 1, 2, 0, 1, 0. and we had our theorem that says that a vertex belongs to some clique if and only if SII is not equal to 0, but SII, those are the diagonal entries. They're all 0. Okay, so there must not be any cliques. So we don't even have to draw the graph to see that, which is kind of neat. Let's suppose that a directed graph has as its vertex matrix M given over here. What are the cliques of the directed graph? So we can compute S the same way as we did before, and in this case we'll get 0, 1, 0, 1, 1, 1, 0, 0, 1, 0, all zeros for the third row, and then 1, 1, 0, 0, 0, and 1, 0, 0, 0, 0. You can double check that a little bit more slowly. In any case, you cube it, and you'll get 2, 4, 0, 4, 3, 4, 2, 0, 3, 1, 0, 0, 0, 0, 0, 4, 3, 0, 2, 1, 3, 1, 0, 1, 0. And this tells us that the first diagonal entry, S11, 3, is not 0 because it's 2. S22 is also 2, so that's not 0. And S33 is 0, so we can't include that. But S44 is 2. S43 is 2, that is. And that's it. All of these are the non-zero ones. So for S113, we get P1 in our clique. And for S22, we get P2. And for S44 of 3, we get P4. So that's our clique. A dominance-directed graph is a directed graph such that for any distinct pair of vertices Pi and Pj, either Pi goes to Pj or Pj goes to Pi, but not both. So there's a theorem that says that in any dominance-directed graph, there is at least one vertex from which there is a one-step or two-step connection to any other vertex. Let's prove it. Consider a vertex. There may be several, with the largest total number of one- and two-step connections to other vertices in the graph. By renumbering the vertices, we may assume that P1 is such a vertex. Let's suppose there is some vertex Pi such that there is no one-step or two-step connection from P1 to any of the other P's, Pi. Then, in particular, P1 to Pi is not true, right? So that means that by definition of a dominance-directed graph, it must be that Pi goes to P1. So next, let Pk be any vertex such that P1 to Pk is true. Then we cannot have that Pk goes to Pi, as then P1 would go to Pk, would go to Pi, and that would be a two-step from P1 to Pi. So thus it must be that Pi goes to Pk. That is, Pi has one-step connections to all the vertices to which P1 has one-step connections. The vertex Pi must then also have two-step connections to all the vertices to which P1 has two-step connections. But because in addition we have that Pi goes to P1, this means that Pi has more one-step connections and two-step connections to other vertices than does P1. However, this contradicts the way in which P1 was chosen, so therefore, it's a contradiction. There can't be any vertex Pi to which P1 has no one-step or two-step connection. Okay, kind of cool. Let's use that. Suppose that 5 baseball teams play each other exactly once, and the results are as indicated in the dominance-directed graph of the figure. Let's use that theorem to show that P2 must have a one-step or two-step connection to any other vertex. So what we'll do is we'll write out M, and we can see that P1 goes to 3, and that's it for P1, right? You have to be careful to look at those arrows. Oh, well, actually, P1 also goes to P4. Okay, fine, so that's 2. So we have 0, 0, 1, 1, 1 for 3, 1 for 4, 0. And then P2 goes to P1, so 1, 0, 1, 0, 1. then P3 only goes to P4, and P4 only goes to 2, and P5 goes to 1, and to 3, and to 4. Okay, let's construct a matrix A equal to M plus M squared. So I'll rewrite M 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 0, 1, 1, 0. And I'll add that to M squared, so I'm adding that to 0, 1, 0, 1, 0, 1, 0, 2, 3, 0, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 0, 1, 1, 2, 0. And I get 0, 1, 1, 2, 0, 2, 0, 3, 3, 1, 0, 1, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, 2, 3, 0. So for the top row, we get 4. For the second row, we get 9, just adding up the columns. Then we get 2, and then we get 4, and then we get 7. So 9 is the highest number, so that means that P2 must have a one-step or two-step connection to any other vertex. It's possible that P2 is not the only one by the process we did, because all we did was take the number of one-step connections and add them to the number of two-step connections to get the total one- and two-step connections for P2 and show that that's 9. But it's possible that, a smaller number of one- or two-step connections could have sufficed. However, we have the theorem that says that there must be at least one, so it's guaranteed that the one with the most number of one- and two-step connections would satisfy that condition. The power of a vertex of a dominance-directed graph is the total number of one-step and two-step connections from it to other vertices. Alternatively, the power of a vertex pi is the sum of the entries of the ith row of the matrix A equals M plus M squared, where M is the vertex matrix of the directed graph. So we could think of vertices as being powerful when they have a higher number of connections. So let's rank the 5 baseball teams in example 7 according to their powers. Well, we already computed the powers by adding M plus M squared. So we could say that the power of the team P1 is equal to what we got when we added up all of these guys. So that was 4. It had 4 one- and two-step connections. So we could say that that power is 4. Then the power of team P2 would be 9, because that added up to 9. The third row of the sum added up to 2, so that's the power of P3. And then the power of team P4 would therefore be 4. And last but not least, the power of team P5 would equal 7. So if we're ranking them, P2 has the highest power, followed by P5, followed by P1 and P4. That's a tie, and because they both have 4, and then followed by P3.